universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hey, hey.
Hey,
Hi,
hey, hey.
Tara.
Hi, how you doing? Good
I'm
to see you.
okay. Hey, everybody, welcome to Sky Tour Radio. I am Mark D'Antonio, and you know who that is. That's Tara.
Hello.
And tonight, we are at our new place and time. We are running from 8 to 10 on Wednesday nights now. And that's going to give us a chance to do more live shows because the weekend sometimes gets crowded. And so we've had to do replays. Absolutely don't like doing those. So now we have a better opportunity. And she demanded it anyway. It was
Yes,
her.
that's right.
She wants to be seen on camera all the time.
No. I want to hear about the universe and all the secrets. But I want answers if you don't mind.
Oh no, you're absolutely right. And tonight we're gonna do that. My shirt actually says that. I mean, I have answers on the shirt. But and I was telling Tara earlier, I've used all these equations at one time or another. Mostly another. But the tonight is Sky Tour Radio's debut, as I said, and tonight we're gonna do a little it's sort of a presentation, but Tara and I are gonna go back and forth on a bunch of things. We're gonna be talking about planets around other stars, exoplanets, and I'm gonna give you a little bit more data than I've ever given you before on this. We've never gone down this particular path, and you'll get to see a little more detail what we're talking about. So before we do that, what's that?
No tests later, is there?
Oh no.
Okay.
Yes.
Okay.
No.
Oh, it's a pop quiz. Okay.
No, yeah, pop quiz, right? Yeah. As soon as the quiz comes out, you pop out of the room. No. So I just wanted to share with you, for those that saw the video I produced of the Benson site, I put it up on Facebook, I believe. I don't know if you got to see that, Tara.
I'm not on Facebook.
You're not on Facebook, yeah. And it was big, so I couldn't just send it. That was part of the problem. So, just wanted to show you some of the photos. When you go out to the news site, we have Sky Tour live stream remote observatories, as you know, and STLS-1 is out in the Sonoran Desert. Okay, it's west of Phoenix by about 75 miles. Tara knows the site well.
Mm-hmm.
She's been out there 1,000 times. Without her, that would never have been set up. Her and Marianne, Rob. It would have never happened.
It was fun to do, though. It was very fun.
Yeah, and now we have a second site, thanks to the people that provided donations and stuff to help us, because we are a 501c3 nonprofit organization. Also, thanks in part to that one over there, we couldn't have done it without her either. And the Benson site in Benson, Arizona, is actually a site where we're on a high plateau, and there's 10 observatories up there, and actually 12 observatories up there, and there's 10 in a long row, and that long row looks like this. Okay.
Wow.
Each of those cubes that you see are an observatory where the roof rolls off, and telescope inside can now peer up and look at the sky and do its thing. The closest one here in this picture, which is right there to the this way here, okay.
The other hand.
Yeah, and the other hand, this one right here, okay, is this is a door to a storage closet, and where I'm actually with my hand, that's our observatory is a little bit more this way, but that one right next to us that you see past that door, that is a very active astronomer who's on almost every clear night. He's doing analysis of the night sky, and And then further down, there's another astronomer that has a telescope in there. I've seen him and met him. Now, the thing that's interesting when I say seen them and met them, these guys are all running remotely from wherever they are in the country or even the world. And so I'm in Connecticut, okay, and I'm running the one in Benson, which is about 2,500 miles away. And so I run it from here. But then we have the one in the Sonoran Desert, which is about 2,600 miles away. But I run that from here too. And many times, if I have Benson open, I have the Sky Tour Sonoran open as well. And we have two different telescopes, right? We have the wide field one that shows big, giant, expansive views of the sky. In fact, the picture behind us in this image here, okay, this big, vast picture behind us, it was taken with our Sky Tour Sonoran telescope. The Sky Tour Sonoran telescope with that wide field, it's 3 full moons across and 1 full moon tall, 2 full moons across and 1 full moon tall in size. And we see that giant swath of sky. So we get all these nebulas and all these things very, very quickly. The telescope runs very fast, photographically. The Benson telescope, on the other hand, that one's a little more technical because we have a much smaller field of view. So we would only be looking at a section of this nebula that we're looking at here and behind us, okay? And these images would be or would be shown at the same time as we're looking at, say, this wide object. We'd show a close-up of that same object, and we do in the Benson telescope. So they have both options, and people watching from wherever they are. We've got people from China, Thailand, Colombia, Chile, Mexico, United States, of course, Japan,
down under.
Yeah, Australia. That's right. You got some there. We got folks from down under. All right. And, those folks, wherever they're watching from, they get to see two views of the same thing, one close up and one a much wider field view. And we make all those photos available to everybody for free. Now, the benefit of giving them away for free is because they're the raw photos, the photos we take out of the camera, and they just get saved up to our server, which you have access to. And our server is located at a place that everybody knows, and it's skytourlive.org right there. Okay, that's our portal. And so we make the photos available to everybody. And when they see these photos, they're free to download them. But if they join our Patreon and they end up coming in and subscribing monthly to us, then what we do is that's effectively you paying me and several other people that we have to process the photos and produce highly competent finished pieces of art. Okay, we don't jeopardize the data. So you could use it for scientific purposes. In fact, one of our viewers is using our data, okay, in conjunction with another professional astrophysicist's data, and is finding stars that seem to have been missing. And what she's doing is she is actually correlating the old historic plates combined with viewing our plates, combined with viewing this astrophysicist's plates, and seeing the differences and seeing what's going on and what has been going on historically in these regions of the sky. It's amazing how things change.
How fun that would be to do. I mean, it seems like it would be tedious, but it'd be interesting, really.
It is, and people know her as Isabella in our chat, and she is one of the most dedicated people. She wrote our app, which will be on the iPhone, Android, and PC and Mac. Okay, we already have it on the PC just as a test base. I've got it on my phone as a test base too. And we have all of our observations for all the years we've been doing this, almost all in one place. You can search every time we photograph this thing behind us right now. This is the Lagoon Nebula over there behind Terra, and behind me is the Chinese Dragon Nebula. It's a summertime sky object. Well, you can go look up every single time we photograph them and look at all the pictures of the times we took. And then you could compare them to each other and see what's different. You might find an asteroid, okay? because an interloper in there would show up as like a little star, little dot. Okay, and if it's missing from one of them, and it's in the other, well, you found something that wasn't there because they weren't taken at the same time. They were taken usually months apart, so or even weeks. So it's pretty cool, and so we can do real science now with our Skytour Live telescopes, and if all goes well, we'll be able to have a spectrograph in addition on our Benson telescope. Now, what's a spectrograph? Well, if you look at the sun, if you were just to look at the sun,
don't do it.
Don't do it. But
don't look at the sun.
If you theoretically, hypothetically look at the sun, you'll find that you take a prism and you'll see that the sun's light breaks up into these colors, right? Red, orange, yellow, green, blue, indigo, and violet. Okay, we call that Roy G. Biv. All right. Now, if you can generate those colors, one of the things you'll see with the sun is that there are lines, the vertical lines in that spectrum as well. Now, what are those? Okay, well, I can show you. Here is an example. The light source, the source of light right there. That's the sun's
hot
core
source. Yes.
Yeah, the hot source. That's right in my face. Okay, that hot little source. That's the sun's core. And then that next thing that says gas right there. That's actually the outer atmosphere of the sun. The core of the sun is, over 10 million degrees Celsius. Okay. And this gas is only about 10,000 degrees Celsius. Okay? Or so. And so what happens is when the hot radiation passes through a relatively cooler gas, that relatively cool gas will absorb some of the energy and make what we see on the right there, an absorption spectrum. We'll see dark lines. Now, what are those lines? Those lines are lines that exist from the chemical compounds in this outer, I should say the nuclei of these atoms. The atoms can exist in this hot gas. It's all plasma. The nuclei are absorbing some of this energy. And like, for instance, hydrogen atoms absorb in a specific location in the spectrum. Calcium absorbs in a specific location in the spectrum, et cetera, et cetera. So where they appear in the spectrum is absolutely dependent on what element we're seeing. Okay. It's almost like a fingerprint of the star. All right. And in our star, it's so reliably the same, we call it the Fraunhofer spectrum. It's actually a spectrum that has been seen ever since we were looking at spectra of the sun. Now, if you look just at the sun without, if you look only at the hot source, we'd see just the colors like this that I showed you. Okay. But we don't. We see this because we're always, not that. Okay. We see this because we're always looking through the outer shell of the gas around that hot core. Now, if you could actually look at just the hot gas on the outside of the sun and block out the hot core, then you see different lines. You see things called emission lines. These emission spectra, okay, and I'll take this so you can see it. These are emission spectra. Again, hydrogen and helium and calcium and magnesium and potassium, they all have a specific place in the spectrum that they show up. Oxygen, and so we would see them look like a bright line spectrum. Okay, so you'll notice notice the line of sight thing. If you're looking at the hot source and then you're looking at this cooler gas to the right of it, right, and the hot source is behind it, you'll get the absorption spectrum. You'll see dark lines. And if you actually look at the gas alone, you'll see emission spectrum. Okay, an emission spectra. And this is something very, very important. And so, go ahead.
Quick question. So is that how you know what you're looking at if you're looking at something in deep space, if it comes back as a black line or a colored line? Can you tell if you look through gas or?
Yes, that's a very good. A very good question. And let me show you another chart to show that.
Okay.
Okay. When we look at stars, other stars elsewhere,
Mhm.
well, what we'll see at the same time is we're going to see absorption lines from them too, because we're looking at their stellar cores, which are in the middle, and they have that outer shell of gas, and all that's coming to us is the absorption spectra. So if you look here, okay, you may recognize the letters on the left side. If we get
Mm.
rid of the numbers,
Oh,
O,
I'll be
B,
a
A, F. Yes,
good
go ahead and say it.
fella and kiss me or something.
Oh, be
What?
a fine girl or guy, kiss me, right?
Yes, that's what I meant.
That's what
Yeah.
we learned when we were getting our astronomy degrees. They said it tongue in cheek. It wasn't actually something we had to memorize. But and
But
within
you did.
those, we did, well, yeah, obviously, because it was silly. Um,
Yeah.
yeah, and so within each one of the stellar spectra, like O stars are the hottest and the bluest, okay? And the B stars are next, all right? The A stars are next, and then of course F, G, K, and M. All right. Well, if you look, each one of those each one of those letters has a 1 through 9 rating, okay, an O0 through 9 rating, okay. So
Okay.
an O1 star would be literally probably one of the hottest stars in the universe, because those are
Mm.
the hottest and bluest. And then an M9 star would be one of the coolest and dimmest stars in the universe. But you'll notice that look at that absorption spectrum there, right?
All those black lines, you mean?
Yeah, those are the
Yeah.
black vertical
Mhm.
lines. Again,
Mhm.
the elements in the outer atmosphere of the star absorbing some of the energy coming from the star's hot core. And as it passes through that relatively cool gas outside the core, it steals some of the energy. And when it steals some of the energy, it shows up in the spectrum as a dark vertical line. And that's
Hmm.
the absorption spectra, because the elements, those atomic nuclei in the outer atmosphere of the star, are absorbing some of that energy. You'll notice that we have in some of the red stars, okay, like right down here, you see the red star right there, M2,
Yeah.
okay?
Okay.
The M2 star, look at all the dark lines in there. But notice also, if you look carefully, you can see that we also have titanium oxide, TiO. That's a molecule, right? And usually
Wow.
you don't get molecules in the outer atmosphere of a star, because the stars are extremely hot, and the temperature is so high that the gas in the star is almost always a plasma,
Mm.
okay, except under certain conditions. All right. Now, what's a plasma? A plasma is when, let's say, you have a hydrogen atom. Okay. A hydrogen atom is a proton and an electron, right? And that's all there is, just a proton and an electron. Okay. There's more
Okay.
stars. Okay. So, a proton and electron, well, if you hit it with high energy, the proton gets hit with high energy, the electron gets hit with high energy, the
Mhm.
electron absorbs it and leaves the atom. It's called
Mm.
ionization. And that ionization process will take the electron off the atom, and now all that's left is the proton running around. Okay, and the electrons are all freely running around them and everything. But the temperature is too high to allow those electrons to come back in.
Mhm.
So they just keep going around and around and around.
And
And
they're
most
glowing, right?
and they're
Are
very,
they
very, yes,
glowing?
that's correct. And
Mhm.
so and that's why if you look at them just alone, that's why you would see the emission spectrum down here on the
Mhm.
bottom there.
Mhm.
Okay, you'd see an emission spectrum. You'd see stuff characteristic of hydrogen. You'd see stuff characteristic of other elements too. Okay. Now, the thing is, those protons running around with the electrons zipping all over the place, those are free. And the sun has this radiation pressure. It's pushing out, pushing out, pushing out all this stuff. And it mobilizes these protons and electrons to leave the sun and race away. And they
Mhm.
race all out into space in all
Yeah.
directions. And especially when there's a solar flare.
Mm.
Okay, a solar flare is a giant expulsion of this energy, boom, out into space. And if it comes right at us, okay, we have a couple days and then we get hit with many protons and electrons from the sun. And that's called solar wind. And when you
Mhm.
have a lot of it coming at you at the same time, that's a coronal mass ejection from a flare. So a big flare shoots this stuff off. And if we're in the position where we're in the line of fire, well, then we're going to get hit with all these highly charged particles. Remember, protons are +1 charge, electrons are -1 charge. When they leave the sun, they stream at high speed to our planet. Can't remember which equation that is in here, but but when they get here, they spiral around our poles, and as they come down to our pole, they will interact with our oxygen and nitrogen molecules in the atmosphere and cause the aurora borealis, the northern lights. And down in the South Pole, the aurora australis. So we have, you've seen many nights recently in the last few months where people as far south as northern Mexico have seen auroras, right? And that's because of the high amount of this protons and electrons streaming off the sun and hitting our planet, okay, from a coronal mass ejection. We just were in the fortunate position where we could get hit by it. Now, if we get hit by a lot of it, that's a lot of charge. And when it dives into the ground after reaching, the poles, dives into the ground, travels through the bedrock, and especially in the northern hemisphere, it travels through, and because there's not a whole lot of population in Antarctica, it doesn't really matter. But in the northern hemisphere, we've got Europe, we've got the United States, okay? And, this is a problem. So once those charged particles get into the bedrock, they travel and they knock out electrical systems, they knock down power grids, okay, sometimes. And there was a famous one called the Carrington event, which is really, really, really strong, powerful flare that led to tremendous power outages. And I have seen full sky auroras right here where I live in Connecticut. And on the same night we had a full sky aurora just a few months ago, I checked out our Sonoran Sky Tour live stream telescope because I have an all sky cam there, and it records all night long and makes a video at the end of the night. And guess what I saw? Auroras dancing around in the northern horizon. It was beautiful, even from Arizona. So, okay, so that's the charged particles that are out in the sun. Those are the things that are responsible for absorbing energy, the different types of elements in the outer atmosphere of the sun that give us the different absorption lines that we see. So this all goes to say that, if all goes well, this is our telescope out there right now. This telescope, we're going to add what's called a spectrograph to the system. And that's going to be one that will actually allow us to look at nebulae, supernovae, and stars, and be able to get these kinds of results and see the different dark lines that are created by different types of stars. And these are very instrumental. These can actually help identify all kinds of things. We'd be able to identify, for instance, different types of supernovae. From a distant galaxy's light, we could look at that and see what elements are present in its spectrum and say, aha, that's a type 1A supernova, okay? Where you have a white dwarf sitting by a red supergiant, and the white dwarf goes off under certain conditions. That's a type 1A supernova, Roman numeral 1I, A, little a. So type 1A. And so we'll be able to identify that. And that allows us to do some very valuable confirmation stuff. So that's kind of cool, So that telescope is up and running. There it is right there. Oh, wow.
So tall.
Yeah, it's tall because I want it to be able to look, close to the horizon. As an astronomer, we don't ever look to the horizon. We always look at an angle that's high enough because we don't want to have to go through what's called air mass. The amount of air between us and the distant stars rises dramatically when you start to take into account you're looking through the curve of the Earth as you're looking in the distance. So near the horizon, things are always flickering. They're never really quite focused. But there are some objects that I'd like to show people because I'm an outreach astronomer. I want to show people stuff in the night sky, as you know this. And so I want to be able to show them the really cool stuff that's out there, even if it's not the best focus,
Where else can you see stuff like that?
I know, that's right. Now, as an example, I was doing some testing. Actually, this is from a live stream, okay? All right. Now break down the screen here. On the left, you see two of the galaxies in the constellation of Leo. Look at all the detail in those galaxies.
Amazing.
This is just a 25-second photo.
Wow.
Okay. On the right, I have another application just sitting up there right now. Normally, I would show the galaxies full screen so people can see all the wonderful details. But this gives an illustration of what's going on at all times. On the right, that's a guiding program that we use, and those you can see on the far right there. There's a little gray square with a white fuzzy thing in the middle. That's a star image, and we're guiding on that star image. And so we aren't. The telescope is. We have it automatically guiding, and it works very well. And so we stack images, all right. And so this image here that you see in the image the photo, that's 22 images that have been laid on top of each other, okay. And those images that are stacked like that, what happens is when you stack images on top of each other, the individual noise from each frame gets averaged out over many stacks of images, and so we create these dynamic stacks, and then those are the pictures we make available to folks if they want a very highly developed one, a highly specialized one that really looks good. Well, then you can again join our Patreon. Yeah, join our Patreon.
Do it now.
Yeah, do it now. And if you act now, yeah. So there's a lot going on now. As far as the other stuff that's up on that mountain, when I showed you this picture here, okay, to the left of that dome, you can kind of see another building there. Okay.
Okay.
It's a little bit to the left. It's kind of right
Shorter.
there. You can kind of see the top of it kind of over there, you know. Okay. That building has about 30 telescopes in it. And it's a gigantic roll-off roof, a 30 by 30 size, foot building. And the whole roof rolls right off, exposing all these telescopes. But the telescopes are just you can't even walk through there. It's so it's so cluttered. But the telescopes are all facing, specific directions, and they don't move. Now, what would be valuable? What would be valuable about that? Okay. Well, the answer is actually something that, if you think about it, it'll make sense. And that is that we have special types of satellites. We know about different types of satellites. We have satellites that orbit. You can see them move through the sky. Okay. Every night at sunset, you can see many satellites, including the International Space Station.
Yes.
But we also have satellites that are stationary over one point on the Earth at all times. Those are called geostationary satellites, or geosynchronous, geostationary. Not quite the same thing, but they basically mean that the geostationaries are the ones that are over one point on the Earth at all times. Okay, and those are 22,500 miles up in altitude. That's where they are in their orbit. Why that far out? Well, when you look at the internet, 22,000 miles.
Okay.
Wow. Now, the reason for that is when you look at a satellite going over, you see it move, right? And then it fades out, right? International Space Station, bright yellow, then it fades out. Okay. Starlink, sometimes in trains of 20 or 30 or more. Okay. Then they fade out. Well, the reason is because they're in lower orbits. And when you're in a lower orbit of only a few hundred miles, then you have to orbit faster to stay in that perfect circle, because an orbit is the exact combination of just enough horizontal movement to counteract the pull of gravity trying to pull you down. And if you do that all the way around the planet, you can move in a perfect circle around the planet. Okay, you're going this way as quick as you're being pulled down by gravity. So it balances you into a perfect circular orbit. So the International Space Station is in a circular orbit, and it's at an altitude of 252 miles. above our heads.
Mm.
Okay. Now, when the astronauts, when the astronauts Butch and Sunny were rescued the other day, okay, it took the rescue ship 17 hours to get to them. Why? They're only 252 miles up. What's that all about? Well, the problem is that once they get into orbit, they have to reach the orbit of the space station. Okay. Then they have to start moving toward the space station, and they do it slowly. So the time it took to get up there was 17 hours. Can you imagine sitting in a chair for 17 hours?
Oh,
Probably not.
no. But if you're in space, I would do it.
And what is it about space that would make it less of a problem on your buns?
Well, there's no gravity, right?
Yeah, you're not feeling you're not
Mhm.
you're weightless, so to speak. You're
Yeah.
in microgravity. So you don't feel it. You just sort of like, it's probably, hey, this is really enjoyable. So it's a little bit more fun, and not as stressful and taxing on the body. And it's just
Mhm.
sitting still in a chair. So it's easier to sit still in space. You know, in fact, they encourage you to sit still. When you sleep, you
No,
put your hands
no
in this
running in
little.
space. Don't run.
Well, yeah, they don't run in space. That's right, because you're gonna go like this. You're not gonna go anywhere, right? But they put these elastic bands on you so you can run like you're jogging on a treadmill, and as you jump, they pull you back down, and they simulate gravity. So the astronauts have to do an hour a day up in space to keep their muscles active. Otherwise, when they get back down here, they'll be blobs
Yeah.
because being out of gravity for a while makes you really weak. You know,
Oh, I can't
so.
imagine their 8-day mission and all that time, how weak they must have been. Because it's not like they planned for such a long trip. So,
No, they weren't planning 9 months.
yeah. How
Yeah,
fun though.
yeah. So the thing is, people say, "Well, why weren't they brought home earlier?" Well, here's the problem with that. They were part of the Boeing Corporation's Starliner program. The Boeing Starliner system has different types of spacesuits than the SpaceX Dragon systems have. Why didn't they communicate? I don't know. I think everybody's trying to carve out their own little piece of space. Okay. But the bottom line is that they couldn't just fly back in a Dragon capsule, which there's one docked on the space station. Why couldn't they just get in and go home? Because they have to be in spacesuits on the way back. They have to plug in. They have to do all the things they have to do. They couldn't do it in the in the Dragon capsule because they didn't have SpaceX spacesuits, which cost, by the way, custom made for each astronaut, $12 million a piece.
You're kidding. Oh,
So
I could
this
not.
last mission to the space station delivered Butch a SpaceX spacesuit, and Sunita was able to wear one of the other SpaceX suits because she managed to fit into it. Um, Probably not the most comfortable because it wasn't tailored to her exactly, but she was close enough that it was okay for the ride home. Um, so technically, she could have gone home earlier, but Butch and Sunny were pairs and they were on the same mission, so they went home together. So interestingly, so when people say, "Well, they could have come home anytime," no, they couldn't have. They couldn't have because they didn't have the spacesuits to ride in the Dragon capsules. This is a call from me to generalize and make a uniform code of spacesuit construction so that
Yeah.
everyone going to space, Russians, Japanese, Israelis, okay, Indians, Americans, all right, and of course anyone else will have a spacesuit that is the same type of generic construction instead of having all these trademarked and copyrighted and patented, outlets and connectors and all. Never, no, forget that. Just
They-
make it one generic thing.
mm. Well, then in the movies, Mark, normally they have like 5 or 6 spacesuits just hanging right there in the closet. So I don't know what the problem was. So,
I know at $12 million a piece, they didn't have they didn't have that many extras. They had one extra, and that was for someone that was on the station, but that person was going to be staying. So the next Dragon mission will bring up yet another one for that person. $12 million a piece.
it's only nice.
Spock, that's ridiculous, right? That's a lot of
Yeah.
money. So clearly, so now you get a little better picture, right? That's something. That's unfortunate. Right now, we'll standardize at some point. I guarantee it. And then, in fact, this incident probably will make it so it happens.
Mhm.
So that's pretty cool. So, but from here on Earth, we can only look up through the atmosphere. And it's interesting. I used to work with the late great Douglas Trumbull. Okay, the guy that did Blade Runner, Star
Genius.
Trek, the motion picture. You know, um, um, Close Encounters of the Third Kind, 2001: A Space Odyssey, and uh, Doug and I were very good friends. And one of the things that he wanted to do was create 3D movies, and so he started. And we actually put together technology. I worked with him, not as I was an underling, just doing yes sir, whatever you need, sir, kind of a thing. But he created this beautiful 3D video from on board the ISS. And when you look at the screen and you see things in 3D, it's a very different understanding, a very different feel, a very different visceral connection. Okay. So we're looking out of the cupola on the ISS, which is that nice paneled window set, and you look out, and there's a Soyuz capsule hanging right nearby, and you can see it there. And we're going in orbit around the Earth. The Earth is going by. You see thunderstorms, you see auroras, okay? But you're seeing them in 3D. You're seeing that auroras aren't just flat lights in the sky. They're billowing bands that have depth and height. Oh, incredible stuff. And this is something that all astronauts feel when they look down at the Earth from above like that. It's called the overview effect. And for those of you watching, watch and look up the overview effect. You'll find Doug's name in there because he took part in this. And the overview effect is why when astronauts come back, in nearly all cases, they come back saying, what are we fighting for? Why do we have such differences? When you see the Earth from space, there's no borders, there's no walls. It's really just a beautiful, impressive ball of blue.
It's a different perspective.
Yeah. Yeah. And then you look at the height of the atmosphere is like 100 miles, maybe. Okay, just about. When the sun's very active, it gets a little thicker. When it's not, it gets a little less thick. But up there, we look at contrails in the sky from down here, right? But from up in the space station, you're looking at contrails effectively 250 miles away. So they're the tiniest white lines. You don't even see them. And they could be covering your skies, but from the space station, you can't really see them unless they broaden out into clouds, okay, over time, which happens. It's part of the contrail science that a lot of the chemtrail people would rather not have to pay attention to. It's an inconvenient truth for them. So it's just so interesting how this all works. And so the view from space, when you look down from above, it changes your perspective, and even though I've never been up there, I want to. Yes, I would do.
You do.
Okay. Yeah, you'd go too.
I would.
If I can think of, I'll save you a seat on the Dragon capsule.
Oh, same here, okay? Yes.
Yeah. Well, nice thing is, if you think about the genius of Elon Musk, he's created a fully automated system. When Sunita and Butch got in that capsule to come home, it was automated. It came home all by itself. They just had to sit there and go, wow, look at the view. If you remember the Apollo era, the button panels on the Apollos, all these flip switches, push buttons, covered switches, do not press. I mean, all these different things that could go wrong, and a gimbal joystick that you could hold with gloves on. Oh, there's actually a game out there that is you have to learn how to use that, and it's sort of like a re-entry game where you actually re-enter in the Apollo capsule of that era, and it's like only someone who wants to punish themselves trying to actually learn this stuff would actually be successful at it. I'd burn up every time. Okay, I haven't tried it, and I don't want to because that's not interesting to me.
Well, even if you survive, it looks like you burn up. I saw how scorched that capsule was.
That's correct.
Incredible.
Well, remember they're
Oh,
going
wow.
from they're going from 17,500 miles an hour. And what they do is when they separate from the space station, okay, they're going 17,500 miles an hour. They hit thrusters, okay, to slow them down in their orbit, and they're automatically going to start dropping, okay, because at a different altitude, your orbits are different speeds. So when I was talking about the geostationary satellites, the farther out you go, the slower the satellites have to go to stay in that circle, okay, because gravity's a little weaker. So if you're near the Earth, you got to go faster so that, for all your horizontal motion, gravity's pulling down a little stronger. You got to go faster to stay in that circle. The station, with its very gossamer solar panels, is moving over 17,000 miles an hour, right? That's really fast, and people can't
It
comprehend
looks
that
like it's
sometimes.
just still.
Right, because you're moving at the same speed when you're up there.
Yes.
So as you undock, okay, if you do a burn with your retros to slow down your forward motion, you're just going to start dropping because gravity's going to start pulling you. And now you're going to enter a gradual lower orbit, lower orbit. The station's going to be going away from you over your head. And you're eventually, when they time it just right, a certain number of seconds, a certain attitude, a certain amount of burns, a certain amount of another orientation, and you'll end up coming back to Earth exactly where you want on the planet Earth. And they calculate with the celestial mechanics, they calculate exactly where that is. So they go around the Earth a few more times, getting lower and lower until finally, as they start to hit more and more atmosphere, they turn the capsule backwards because the heat shield's back here, and it can go backwards into the atmosphere, and it ablates, it ablates all that stuff so that the capsule is protected as it's coming back into the atmosphere. You like that? That's kind
I
of cool,
did.
huh?
That's great visuals, Mark.
Yeah, great visual. These are my flames. Okay. And the capsule is protected, but it has a heat shield on it, so it's protected, you know. Um, yeah, I know that there have been accidents. The Soviets had accidents where one of their Soyuz capsules didn't come back in, didn't orient right, and this high temperature of over 3,500 degrees Fahrenheit burned through the capsule and killed the cosmonauts. Okay, now and it landed fine. And when they opened it up, they were met with a horror scene. So that happens one time, and then you fix that. There was one other case where the capsule was compromised and all the air was taken out way up in orbit, and the single cosmonaut that was in
that
it,
woman?
I don't remember. I think it was a guy, Komarov. Okay, he ended up getting killed, and all that was left of him was a little tiny crispy critter, unfortunately. Yeah, so heat shield failure is a big thing. So obviously, space is dangerous, and astronauts the most dangerous occupation there is. You know, and there's a few things if people want to try it. There's a few things people can do to enjoy the potential for to enjoy the potential for going to space, and we'll
Yeah.
come back to the subject matter in a minute.
Okay.
But just a little further aside, there's an aircraft called the Vomit Comet. Now it's given that name because it's an old aircraft, and they've gutted the interior, put padding the whole length of the tube, and you go in, you lay down on your back, it takes off, goes up into the sky, it's climbing like this, okay, for a long time. Then as it gets to a certain point, it goes over the top of a parabola. Remember the geometry shape of a parabola? Goes over the top. As it does that, you rise up off the floor because now you're feeling microgravity for the first time. It's that feeling you get when you go over the top of a roller coaster hill, just as you drop that, your stomach. That's how they feel all the time. And that's why some astronauts can't acclimate to that. It's scary, isn't it? So I'd give it a shot. I'd give it a shot. I
I
think
like
we will.
scary rides. The zipper, that'll ride the zipper a few times. That'll get you set for space. Right?
Yeah, the Vomit Comet though is cool because they do that arc, and it lasts about 14 to 20 seconds when they do that arc. So you're floating around, and I'm weightless. Whoa, okay. And in that moment, you feel like the astronauts do all the time. And
Mm.
then they tell you, okay, we're coming out of it, and you're going to get back down to the ground and lay back down. And then you feel the weight again, your weight again as they come out of the bottom, and then they turn, they go do it again
Oh,
13 or 14 more times.
oh,
So if you
fun.
get sick on the first one, you're out of luck for the rest of the flight.
Or the people with you.
Yeah, there's about 25 or so people that get to go at a time. Maybe 15, I forget the number. But you're flying a whole jet for just 15 or so people. So it's not cheap. It literally costs you between ten and $18,000 to go for this ride. So it's really only for the rich or for companies that want to get rid of certain employees. I quit. I'm done. Yeah. So
No
it's pretty
more.
neat. Yeah, yeah. So, so I did want to talk about the fact that Sonny and Butch have made it back fine. Um, when you think about it, okay, that fiery passes through the atmosphere, okay, that as they're coming back into the atmosphere like that, okay, that heat shield is what protects them, as I said, but it's also that is air, thicker and thicker and thicker atmosphere. So when they're in the spacecraft, they go from being weightless to now feeling, the ability of gravity to affect them. And as they're getting closer and closer to the Earth and going through this, they're slowing down. As they slow down, gravity's getting stronger and stronger. So by the time they're hanging under the drogue chutes, the ones that come out initially, that just kind of trail up above them while they're dropping, okay, they're feeling gravity again, to some extent. Then when the full mains come out, the main parachutes, there's four big ones. They come out and they stay kind of vertical for a while, and that's called reefing. They have them reefed because if they opened up wide right away,
Mhm.
they could be shattered because that's a problem with they're still moving pretty fast, right? So they reef like this for a while, okay, catch some air, and they're designed to open up more and more and more as they slow down. So once they slow down, all four of them come out. And now the people in the seats in there are going, "Holy cow, man! I'm heavy again," because they're now feeling the weight. So it's pretty interesting how that works. So there's a lot. So that's the effort it takes for us to get off the planet right now. You know, that's the effort. And I know that we've got another hour and a bit here to talk about the other main topic, but I did want to open it up to see if you had any questions about this as well, because I know we also have people watching in the chat. I'd like to
Mhm.
find out if they've got anything they'd like to share
Yeah. Well,
or any questions.
I had a question on like the space thing. How they were stranded up there. They usually plan for 8 days. I know that there's a lot of redundancy on space capsules or spaceships and
Yeah.
systems and stuff. So, what? I mean, how do they plan for like medical things? If someone had take like thyroid meds every day or something, do they plan in advance in case something like this happens, or is it just
Yes.
a
Uh,
resupply mission? You're just at the mercy of that.
well, that's the thing. Okay. Resupply missions resupply some obviously essentials, food that they can't replace.
Yeah.
Now, this is going to turn off a few people, but when you go to the bathroom on the space station, number one, okay, that's recycled and you drink it.
Yeah.
Oh, yeah. And that recycled urine
They like chicken.
is the best water on the whole planet because it's so crisp and clear and clean. Once you filter everything out of it and chill it, you probably would think you're drinking a really nice bottle of a very high quality water.
Mountain stream.
So yeah, it's really yeah, a mountain stream, all right. It's a high altitude stream that becomes drinking water. And things like that you get over, I think, really quickly because you realize that if you don't drink it, you die. So it's very important to do that. um I know that that's one thing. Now the other, well, the bathrooms are very specialized up there, but keep in mind that the astronauts travel in a microgravity environment, so they just kind of float through. So you can imagine that if you kind of went to the bathroom, it's going to go, you know, and when water is set free up there, it tends to form little globs, round balls. Okay. And it's really weird how it operates. I remember I was watching one astronaut took a GoPro camera and a big ball of water, and he pushed the GoPro into the water inside the spacecraft, inside one of the habitats, and it just sat there floating. And the view from inside is like, it's like
That's pretty cool.
you're looking through the water at him. It was the coolest thing, but it pointed out how water operates. Now,
Mm.
um, water operates and water molecules operate using the surface tension. Okay, uh, the minimal area. Okay, and so it means that the shape that would be generated by a water drop in space would be the least. It would require the least amount of energy to maintain, and that's a sphere. That's why planets are spheres.
Mm.
Okay, that's why Earth is a sphere and not flat. Okay, it's not
Are
flat.
you
We've checked.
sure?
Yeah, you know. Um,
Sure
we have a
about that?
break coming up, don't we?
We have in 6 minutes.
Oh, good. Okay, so when we talk about like water in space and everything, so when you actually go to the bathroom in space, you can't just like here stand in front of a toilet and go boo, 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 and aim it, because those drops will splash off of things and go airborne and just float around. They'll go in your eye, they'll go in your ear. It's just not any fun, right?
They go on the
So
equipment.
yeah, they do. They have these special vacuum hoses and things, and you actually use those for both ends.
Mm.
And there's special capabilities that you and special instruments that you use in order to do that. On the space shuttle, it was I have the space shuttle manual here, and the number of steps to use the space shuttle toilet,
Uh-oh.
there's about 75 steps to go to the bathroom. And by that time, you've gone in your pants. I'm telling you.
Plan ahead. That's the thing.
Practice makes perfect.
Uh,
Practice.
no water after 8 a.m.
Yeah, I don't think I would drink at all. It's like, oh, drink this all now, because
Yeah.
yeah. So that's the kind of thing that's fun, right? About the whole traveling through space. Now, I saw a few questions out there. I know that somebody asked, I think it was Donald Kunzer. Did he ask about, and Marianne's here too, by the way.
Mm.
Yeah, I think he asked about radio telescopes. We don't have any radio telescopes out in space. The James Webb is looking at infrared energy, okay, but radio waves are out in that far spectrum, okay, and the James Webb sees far out there, okay, but radio waves we can use here on Earth because we can capture the radio waves reaching us from space, okay, so we don't need to put a radio telescope out in space. But
Mm.
in fact, it was that large collection of radio telescopes all over the planet. Okay, as a planet orbits and rotates, right, as a planet revolves, we had these telescopes at various points on the planet, all looking at a particular location as the Earth was rotating. And that particular location was the center of a galaxy called Messier 87.
Oh.
It was where they saw a black hole in the center. And the thing is, it's so far away that to have a telescope with the kind of resolution you need to see something that small from tens of millions of light years away means the telescope has to be a big diameter. So what they did was very cleverly use the diameter of the Earth, okay, 8,000 miles, with telescopes at various places on the Earth, including Antarctica down there out of the view. And they looked at this object as the Earth rotated. As it's rotating, they're seeing it as they're rotating. They're watching the same object the whole time. So they're catching all this imagery. So now we have this one swath of data for this latitude, one swath of data for this latitude, one swath of data for this latitude, et cetera, et cetera, et cetera. Added together, we get a very rough 8,000 mile diameter set of observations. Okay. Repeat that often enough, and now you get a much higher data set accuracy and higher resolution. And this is how we were able to resolve seeing something 40 plus million light years away out in the middle of out in space. I thought that was pretty cool. And they've done it with the black hole at the center of our own galaxy, which is about 33,000 light years away.
Right.
You know, so clearly that kind of thing is something that is really good for us to do, right? So and we can do that from the Earth. See, we can do the radio stuff from the Earth, but from if we have to do anything else, we want to look with telescopes like our Sky Tour telescopes or Earth-based telescopes. You'll notice they're all on high mountains. Okay, and the high mountains mean less atmosphere to look through. Okay, the atmosphere is about 100 miles thick, but it gets drastically thinner, and by the time you reach about 25,000 feet, you're above about half all the air on the Earth. So if you can get up to like 7 or 13,000, you're actually making quite a stab there. So out at Mauna Kea in Hawaii, they're at 13,700 feet. Okay. People that go there for the first time sometimes need supplemental oxygen. Now, I rode in a Army aircraft as a photographer for an air show. I mean, I wasn't in the Army, but I could ride with the team, the skydiving team, and we were at 12,000 feet and doing all these really wicked turns. And of course, I got airsick on the way down, but I didn't do anything. I just got queasy. But from that altitude, we're going 230 knots, so obviously pretty fast.
Going fast into break?
Yeah, we're going fast. Yeah. But then the temperature where I was sitting was like below zero because of wind chill, but it was 85 degrees in the ground.
Oh my God.
So yeah. So anyway, the point being that, from that altitude, okay, the atmosphere was thinner and I could feel myself feeling lightheaded. Yeah. And I think we have to pick this up on the other side now.
Let's do it. I'm interested. So cool.
Okay. All right, guys. Well, we'll be right back.
Yeah.
Yeah. Right after, these words.
Hey members, the new KGRA DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
As UFO reports come in from around the world, the Mutual UFO Network, MUFON, is there. We continue to explore new cases and build our massive database. We share our information with the world in a number of ways. If you'd like to be part of our investigative team, you are always welcome. What could be more exciting than exploring the UFO question firsthand? Join MUFON, find your friends.
You're listening to the KGRA Digital Broadcasting Network. We provide unparalleled coverage of trending news in the world of ufology, cryptozoology, and paranormal phenomenon. Whether you're watching our video live stream or listening to one of our audio programs, you are getting the best from world-renowned researchers and hosts, guiding you through topics the mainstream won't touch. Miss one of your favorite programs? No problem. Head over to the members area at kgradb.com for access to our massive library of award-winning content. Make contact, stay connected, only at kgradb.com.
Hey, welcome back, everybody.
Hmm.
Yeah. So,
Hello.
yeah, I misunderstood a question in the chat. I think the question was, are there any radio telescopes in Benson at that site? And the answer is no, there's not. Yeah, it's
Good question.
yeah, it's an optical observatory location, you know. But it's nice. The altitude, by the way, is 3,600 feet, which is double what we are in the Sonoran Desert west of Phoenix with Sky Tour 1. That's like 1,900, 1,800 feet or so. But you know, still not bad. I've noticed some significant differences in the night sky during the summer in Benson than in Wickenburg. It's actually that extra bit of altitude. Wow. A lot of air below us, so you know, at least enough so that you can see more detail in the Milky Way than I've ever seen.
Oh, cool.
Yeah. Oof. So, in any case, I was going to take us down a path of looking at planets around other stars and kind of get an idea of the kind of things we've done with all of our technology where we can barely leave the Earth. But I wanted to do one last thing, and that is to talk about a potential problem for us if we put too many satellites into space. Now, yes, we have Musk putting up the Starlink satellites, okay, but it's sort of like a mixed bag for me because our telescope out in the Sonoran runs from Starlink. We actually have our internet due to Starlink. And as it turns out, our Benson location is probably going to need Starlink too, because when you have 10 or 12 astronomers on the mountain all using their stuff at the same time, the internet is a little bit slowed down, and that's not good. So we may put up a private internet network up there through Starlink. I don't want to, but we might have to. And I did want to answer this question from Karen. Does the VLA, well, she means, is the VLA still running radio telescopes? Just a very large array. And the answer is yes. Yeah. And so that is that's something that is going on now. There's something like 22 to 24 radio dishes that are on the plane out there, the San Augustine plane. I've been there. I was there, and with my producer Bill from our show. He was previous producer. He's been there, and these are these big, 80-foot diameter radio dishes, but they're on tracks that they can move and be moved around. So if they move closer, they have a different resolution when they're moved farther apart. And so if you want to see detailed things, you change the orientation of these dishes. And so it's a variable radio telescope, which is kind of cool. Really neat. Variable, So kind of neat.
Awesome.
So yeah, so the VLA is still doing things. And so there's a maintenance shed when you first get there. Off the visitor center, there's a large shed, and it's open at one end. And 9 times out of 10, there's a satellite dish in there being maintained and going through maintenance. And it's 80-foot diameter dish, so you can imagine. Now, if you go for the tour, you actually climb up the ladders and go onto one of the dishes, so you can actually see, from that perspective, what it's like. Really kind of cool. But that'd make a cool photo.
Oh, it sounds great. Yeah. I think
Yeah.
we all should go there. Spring
I know.
break.
Exactly. Mm,
Let's do it. Next year.
next year, yeah. So I wanted to add something up here. This is right here is an exoplanet presentation that I prepared for everybody.
Yay.
And we won't get through all of it, but that's okay. I'm just I want to point out some of the most important parts. All right.
Okay.
And now the bottom line is, if anyone has questions, feel free. You know how I run SkyTour live stream. Well, SkyTour Radio is the same way. If you got a question, put it up there, and I will make sure that we answer it. So, and same goes for you too, down there, Tara. You could be up here too. You don't have to be down there, So yeah, when we talk about exoplanets, one of the things that's important is, why do we look for these exoplanets, right? Well, the idea is that we want to find out if we're alone, and is there life beyond us here? And the most important thing is we're searching for life that's carbon based, right? And that means, by definition, we're going to be finding Earth-like worlds, right? Okay, because the question is, what might they look like otherwise? And that's a question we'll answer in a little while. But think about this. We're carbon-based life forms. Carbon is the fourth most abundant element in the entire universe. The third most abundant one, oxygen. Okay. Second, helium. And the most abundant one is hydrogen. Yeah, you got it. And so with that abundance out there, it stands to reason that that carbon, which is extremely flexible, I mean, carbon can make bonds with and break bonds with more things, millions upon millions of things, more than any other element in the periodic table. So it stands to reason that life is going to be based on carbon. Right now, yeah, it may be carbon bigot. I agree. Okay. So I guess that means that being a carbon bigot, it just recognizes the importance of carbon in the universe. Okay. Now, when we look at the prospect of intelligent life finding us, well, Stephen Hawking once said we should keep our heads down. Don't, stay below the radar, Okay, they're over there, stay down here, hide, okay, peek out once in a while. Okay. That's what Stephen Hawking would like to have us do, remember?
Oh yeah.
This, we've already been out there and we weren't even in control of it. Because if you have a carbon-based life form on a planet, what's something that all carbon-based life forms require?
Talking about water and oxygen, or
Exactly that.
stuff?
Water and oxygen. And we have copious amounts of both, and have had for long before there was life on our planet. Okay, that I should say intelligent life on our planet, right? So it was back, oh gosh, we're talking about 2.4 billion with a B, billion years ago. Billion years ago. And yes. That's when there was something called the Great Oxidation Event, the GOE. Now that meant that at that time, suddenly, and I do mean suddenly, over a few several 100,000 years, the amount of oxygen in our atmosphere skyrocketed. Now, that from an atmosphere that was of a basement levels of methane, carbon monoxide, CO2, ammonia, all right, and so forth, and hydrogen. Okay, that suddenly we had oxygen, diatomic oxygen, two oxygen atoms together, the breathable kind that we use. And why is that? Well, because early in our life here on Earth, I mean, if you look at the picture here, what do you see? Do you see a continent?
Green primordial soup.
Yeah, you see basically a greenish blue, right? You see the clouds, and then you see what looks like ocean, right? So basically, it was a water-filled planet. And so this water-filled planet, with the appearance of continents that came later, was already starting to pump oxygen into the atmosphere, and we weren't even here yet.
Mm.
You know, so there's a lot of things that happened at that time, but one of the things that happened too was these carbon-based life forms that we have here depend on a bunch of things. They depend on things like complex hydrocarbons, carbon-based compounds, and amino acids, right? So we have the basic building blocks of DNA, right? Cytosine, guanine, thymine, and adenine. Okay,
Mm.
those are the four basic nucleotides. Okay, well, those were here. Some were delivered to the Earth through comets and meteors, and as it turns out, they're thinking that maybe comets weren't the primary provider of water to the planet because they're made of ice, right? So you figure, well, maybe a lot of them struck the Earth. Sure.
Mm.
No, actually, there was a lot of asteroids that struck the Earth too that had, proportionally more water
Mm.
than tiny comets would. So the asteroids actually probably did that job. You know what I mean, Tara?
Yeah.
Yeah.
Well, there's so much water. I'm not in it all the time, so it seems like there's more Earth, but it's that the amount of asteroids that would have had to have hit is incredible.
Yeah. There have been a lot of asteroids that struck. And
Mhm.
of course, the Earth also made the building blocks that we benefit from too. And that's what's interesting. So, okay, this is all true. A lot of the building blocks were delivered by other sources, meteors, asteroids, comets. Okay. And the Earth made some of itself. And so the way the Earth made them, now, just as an example, this is Comet 67P, Churyumov-Gerasimenko, the Rosetta mission.
Cool.
That's a comet. That's what a comet looks like up close. We landed on this comet. And the Rosetta mission was an orbiter that went around this comet, took these photos. Okay. The Philae lander, Philae, was released from the orbiter, went down, and it was supposed to latch onto, down here somewhere. It was supposed to latch onto the ground where my cursor is here. You can see it. And it had these little pins that would fire into the ground to anchor it because there's very little gravity on a comet. So if it hit, it would just go boing and bounce off. So it had these little firing pins. Unfortunately, when it hit, it fired the pins and that catapulted it off. So it must have hit like a hard rock, underneath this icy mantle of stuff. And it sent it bouncing up to 15 times across the face of the comet with very low gravity, totally out of control. And it ended up landing in a fissure, and it could be seen from the orbit of the Rosetta mission a little bit, but not much. It's stuck like in a fissure down there, like down in this region here is sort of like a fissure, which you can't really see. So maybe here, kind of like in this region, a dark area. And so you saw it in there briefly, but anyway, you also notice these things, these jets of gas right here. See that? That's
very
not
cool. But there's two of them at least.
Yes, there's
Maybe
actually
one.
several. Notice that there's streams. Okay.
Yes.
Yeah. And that's interesting because what's happening is the comet 67P was getting closer to the sun. As it got closer to the sun, it started to heat up. And when it heated up, this is dust on the comet's surface acquired over billions and billions of years, okay? Because it's been here for 4.6 billion years, and this is how it looked, and successive passages by the sun melt the interior a bit, and then there's gases trapped inside, and it comes shooting out in jets, which causes the comet to rotate a little funny sometimes. And so this trapped gas comes out. Maybe there's carbon dioxide there, carbon monoxide, cyanogen, whatever. But it was trapped in there, these molecules, and they come shooting out at high speed, and they can be photographed,
You know what I see in that photograph?
Tell
Let me
me.
change it. I see a horse's head. I see a horse's
Oh
head
yeah,
looking out
that's
to the
right.
right, and his neck
Us
and his
tonight.
body.
It's a whole body. In fact, here's the
Yep.
horse's back end right here.
Yep. Mm-hmm.
And there's like crows sitting there pecking at his back end right here.
Yes.
Well, that's very good. And just for those that don't know, she's an artist and a darn good one.
Oh, wow.
Okay. So, you know, she's the favorite go-to artist for Sky Tour, you know, as well as everything else she
Fun.
does, which is phenomenal.
Mhm.
That does look like a horse, as you
It
mentioned.
does. How funny.
Wow. Until you said that, I didn't even notice.
Is that right?
You know?
I think it's obvious to me, but
Yeah.
we all see differently, and our parabolic setting
Yeah.
in. So
Yeah.
it's fun.
So this being the closest view of a comet we've really ever had, and more than half of this comet is made up of carbon-based molecules and organic molecules. So you can see why comets delivering material to the Earth was very important in our early formation. Okay, and then meteorites also were very important. This one here is called the Murchison meteorite. This one meteorite that fell brought 90 different amino acids to this planet.
Wow.
Amino acids are the building blocks of life. Spock, they are the building blocks. We have to bring these to our planet, right?
How big was it, Mark?
I don't know.
Okay. They're big enough to hold 90-some amino acids.
Yeah. So within some of these confines, there were 90 amino acids. Incredible. Now, the Earth itself also was able to create these building blocks of life as well. The whole point, if you see where this is going, the building blocks of life are brought to us from all over the universe for many different means. And then the planet itself, provided it's in that not too hot, not too cold zone, known as the habitable zone, the Goldilocks zone, okay, will also provide. And on our planet, we had the luxury of having liquid water on the surface. Now, liquid water can exist on the Martian surface for a short time. As soon as you pour it out of your jug, it'll go down to the ground and go, and in short order, it'll evaporate away. It'll actually sublimate away and go directly from water to the vapor. Okay. The reason it has to do with the pressure of the atmosphere. Okay. Mars is sort of self-regulating. Its pressure is just below the pressure required to have liquid water on the surface. And that's for another night, but I've talked about this before, how the pressure on Mars self-regulates to stay just below that. And it's not magic. It's not some kind of conspiracy. It's actually just the way the universe works. And it has to do with something called the triple point of water. All right. But back on Earth, Earth being more massive with enough of a substantial atmosphere, it was able to retain the pressure with its gravity. It retained the atmosphere, meaning the pressure of the atmosphere was high enough that liquid water could exist on the surface. It wasn't always the pressure we have now, which is 14.7 pounds per square inch. Every square inch in your body, you're getting 14.7 pounds of atmosphere all over your head, all the way to space, pressing down on that 1 square inch. And then you just add it all up. So we have a lot of pressure. You go into the ocean and you dive down to 13,000 feet, like the depth of the Titanic, and you're talking about 6.5 tons per square inch on the body. See, now that's not just the weight of the water, that's the weight of the atmosphere over your head all the way to space as well, plus the weight of the water in that tiny little square inch all the way down to the bottom. Okay, add that up for your whole body, and you're gonna get squished out of existence, right? Now, actually, that's sort of not true. Your body is mostly water, and water is effectively not compressible, meaning that your eyes won't go and go away because they're filled with water. The pressure is the same, right? So the ocean water will be pressing on them, right? And your eyes are used to pushing out at 14.7 pounds per square inch. So with that kind of pressure on your body, water's not compressible. So it's not going to push the eyeballs in, okay? But what it will do is penetrate your sinuses and go all the way in, go in your ears, probably go past the eardrums into all the air-filled spaces, especially your lungs, okay? So the Navy had the bright idea of experimenting some years ago with a highly saturated oxygen solution. And divers that tested it would have to inhale this liquid. In
Oh,
other
that would
words,
be scary.
drown,
Yeah.
allow themselves to be drowned,
Yeah.
knowing full well that they're going to be able to breathe on the other side of that. And they would pump this high saturated liquid through their bodies. And that highly saturated liquid in their bodies would actually allow them to gain the oxygen they require. And that's the one stumbling block to diving deep in the ocean as human beings, right? So we could dive routinely. We'd be able to dive to like 3,000 feet by breathing this solution and go open our canals and our ears and all that. And it was a program that actually kind of worked. You've seen the movie The Abyss where they dropped a little rat
Yes.
in that liquid. Well, that was really done. And that was this highly saturated material. So he didn't die, okay, because he was actually able to breathe. But your diaphragmatic muscle that controls that can breathe air in and out, but it can't breathe liquid in and out. So it has to be assisted. So they would have to pump it through. So they had these big pumps. They tried it, and it worked. But the only trouble was that divers that tried this, you can expect that not all the liquid's going to come out of their lungs. So these divers would end up, for the sake of the experiment, getting a severe case of pneumonia, fluid in the lungs. And so they have to, go through lengthy recoveries if they survived at all. There's not a whole lot of information on this out there, but it was something that was done. So anyway, so pressure on the Earth at the surface is 14.7 pounds per square inch. And then the ocean, of course, is deeper. But that 14.7 pounds, more than enough to have liquid water on the surface. So what would happen is, in the primordial Earth, we actually ended up with this incredible little petri dish here on our planet.
Like
And it was
Bunsen burner.
Exactly. It was a giant Bunsen burner. Okay. And it was the equivalent of this experiment we see right here. This is the Miller-Urey experiment done in 1952. And the Miller-Urey experiment was an experimental setup. It looks just like you see, a glass ball that had water in it. It had ammonia in it, NH3. It had methane, CH4. It had diatomic hydrogen, H2, and carbon monoxide, CO. That was the primordial atmosphere of the Earth as we thought, and still think it was probably likely. All right. There's been changes in the formula here and there, but the bottom line is that's kind of what it is. And so on the right there, you see there's a heat source. Well, think of that as simulating the water cycle on the planet. The water's heated, it's turned into water vapor, goes all the way up that right side, comes over the top, and drops down into this flask. Okay. And in that flask, there's a spark gap. So what's that simulating on our planet?
Like thunder
and lightning. Yes, exactly. Yeah. So this was to test, the Miller-Urey experiment was meant to test whether the Earth itself could create the building blocks of life. And the result after a week was this brown sludge on the bottom of that flask you see there at the left. And that brown sludge turned out to be a incredible amount of amino acids. Okay, building blocks of life formed just through lightning action, as you see here in this diagram. So when Stanley Miller died in 2007, they found 20 more amino acids that they never detected the first time. You're
saying that original sealed vial?
Yeah, that's right. They had the original sealed vials, and when they examined them again with better techniques, they had missed 20 amino acids. So there was a lot. So in other words, Earth creates its own amino acids required as building blocks of life as well. And that's really kind of cool. I thought that was really a neat thing. Now, another oddity, which I think is interesting, is how we're constructed as carbon-based creatures. Think about it. Bilateral symmetry. Who knows what that is out there? I think all of you do. We're the same on the right as the left for the most part. Okay. And bilateral symmetry is potentially a product of how DNA replicates. Now, we won't go into DNA replication. I don't want to go through, the biology with you because that's not what this is about. This has to stay fun.
That's interesting.
But you know how DNA replicates because you're smart about this too.
Is it unzip and just kind of?
Yeah, that's right. One half unzips and another complementary symmetrical side zips in to form the new molecule. Well, at the micro level, that's what's happening. At the macro level, the body has imitated that too. So we have two eyes, we have two arms, we are symmetrical left and right. And it's possibly due to the way the base life form that we are was created, right? Now, that's the thought process. Now, this is true in all higher life forms. Now, it's not true for every life form because we also have radial symmetry, okay? The internal arrangement could be different, but the way the creature works with the environment is through a symmetric mechanism, okay? We have one set of intestines. We have one heart, okay? But externally, we interact through symmetry with our environment. Clever design. Now, but as I said, there's more than that. We have radial symmetry. Consider a tulip or a daisy, right? Lots of little petals all the way around. Okay. And starfish are interesting. They are pentamerous. They're five-sided. They're Echinodermata is the name of them. And they're bilaterally symmetric as larvae when they're first born. And they look kind of weird. They don't look like starfish at all. They look like little suction cups. Okay. But then as time moves on, they become this radially symmetric five-sided creature. So it's pentamerism. So bilateral symmetry is built into the nature of how we were formed. It's really cool. So now the question is, okay, let's suppose there's life elsewhere. We all believe there is. I do. I actually think it made it here. What does Earth-like mean? What does that mean? Well, obviously,
Like us.
an oxygen-breathing creature, carbon-based creature, maybe bilaterally symmetric, right? Something like that, right?
Yeah.
I would think so. Okay. Well, we know that for Earth-like creatures to exist, they need to be in the habitable zone of their star, the one I mentioned before, where you're just far enough from the star that the water isn't boiled off the surface, like on Venus, maybe in its past, or frozen into hard as granite material as on Mars right now, which is just at the far end, way out there. So kind of in that not too hot, not too cold area. That's where we are. Okay. That's the habitable zone. And liquid water has to be able to form and stay on there. Why do we say that? Because in all of our studies, it looks like life began in the water. We come from the water, Now, how do you know you've come from the water? There's a simple reason we know that we were born in the ocean.
Can I guess?
What?
Is it our salinity? Is it our salt?
Yes, you're a genius. Yeah, it's our salt content. Now, our salinity in our skin is not nearly as high as the ocean. I think we're like, 3% or something? And the ocean's higher. Well, the bottom line is that salinity is a vestige, a vestigial remains, actually, a vestigial remnant of our salt, dependence over the years. Now, why salt? There's a big reason for that, and I'll tell you in a moment, but consider this. When we finally climbed out of the water, we had to take a shell of salt with us, salt water, right? Like a turtle shell. So our skin is like a turtle shell. It's made mostly of water, and it has a salinity of a certain amount, like we talked. And so we carry this vestigial remnant with us. at all times, so we can exist out of the water. Oddly enough, we've evolved so far out of the water that now the water can kill us if we go in there for any period of time. That's like,
You can't have
thanks a
it
lot.
all, right?
Yeah, thanks a lot, water. Okay.
Yeah.
Yeah. So so the salinity is interesting, and our dependence on sodium, which is worth sodium chloride, a sodium atom and a chlorine atom together make salt. Table salt, Na sodium, Cl chlorine. Okay. Yes, I know sodium it's not Na, but that's the elemental formula, Na. So capital N, little a, and Cl. All right, sodium chloride. Now, why is that? Well, why is the water salty? As a matter of fact, now that's a very interesting dependency. We had for the longest time, our atmosphere was 90 times thicker than it is now. Venus' atmosphere is 90 times thicker than ours right now.
Wow.
But ours is much thinner now. And the reason is because we're in that habitable zone. So what could happen is we had a rocky surface that had hardened early on, and it was molten for a long time, and then it became hard and rocky. And then because we have a thicker atmosphere here, unlike Venus, it could rain. And when it started to rain, water would hit the land and then run in little rivulets and make rivers, and finally large rivers and gushing waterfalls and so forth into low-lying areas. Over time, over millions of years, that became oceans. The thing that's interesting is when water runs over rock, several things happen. First of all, sodium atoms are easily dislodged from the rock strata, and so are chlorine atoms. And the thing that's interesting is one of the atoms has an extra electron, and one of the atoms needs an electron.
Oh.
So when those sodium and chlorine atoms get into the water, they go bloop and they connect to each other. Okay. And that's sodium chloride. Sodium
It
chloride.
looks like a mask to me, but
If you've been trained. Okay. Sodium chloride. And now that sodium chloride now in certain salinities, and there's different types of salts as well based on the compounds, is what causes the oceans to be salty. And all life forms in the ocean depend on sodium as a result. And so do we. So our vestigial sodium that we have in our bodies is something that was a holdover from our evolution out of the oceans. You know, my shirt says so. No, I'm just kidding. Right. So liquid water was very, very important, as I said. The other thing that was really important is that the star isn't crazy, that the star is not some wildcat that starts shooting all kinds of stuff at us, you know? Yeah, like ultraviolet radiation to go, okay, you're all sterile now. Okay. Ultraviolet radiation does a number on water molecules in the atmosphere. Just look at Mars. Okay. Our magnetic field, which is another fortunate, I say contribution of the formation of the Earth, is that we have a molten outer core and a solid inner core. Well, they rotate against each other and generate electric currents of very, very high amounts. Those electric currents, in turn, make magnetic fields. And we have a magnetosphere, a giant magnetic field around our planet as a result of that core down below. Now, Mars also had one of these. Okay. Mars also had water like we have, right? Mars had a thicker atmosphere. However, Mars is a little smaller, and the electrical charge being generated in its core waned over time because the Martian dynamo, that creates these electrical charges, wasn't as powerful as the Earth's. And over time, it was able to wane and go away. So when that happened, the ultraviolet radiation from the sun was no longer trapped out by the atmosphere. Okay. The ultraviolet radiation was actually, able to penetrate the Martian atmosphere, and the water vapor molecules, H2O molecules in the atmosphere, would be struck by this ultraviolet radiation. Pow! And the hydrogen would be separated from the oxygen. Okay. So you have two hydrogen atoms freed to go to space. Oxygen atoms fall down to the planet. Okay. And now you have this disassociation of all the water molecules in the Martian atmosphere. Okay, again, far into the habitable zone there. And so now, with that disassociation of the molecules, they became H2 and O, right? So fast forward a billion years, and all the water on Mars is now evaporating, and there's no water cycle anymore. It doesn't rain back out. So the water evaporates and goes away, evaporates and goes away. Eventually, you're left with a bone dry, sterile surface like Mars is today. Surface. Notice I said surface.
Right.
Okay. So that's why. And the Martian topsoil is irradiated by ultraviolet radiation. And it's just, there's nothing that can grow there right now. But underneath the surface dust layer is the water that froze, because Mars had copious water, still does. Okay. And the surface water froze and got covered by dust. And once that happened, as the Martian atmosphere thinned out, all right, the pressure dropped, a lot of water sublimated, went away, and much of it, as it got colder, the water froze. And now the water on Mars is as hard as granite. Okay, there was a probe that landed in the northern plains of Mars, and when it took a downward-looking shot where it was landed, the jet of the exhaust of the landing jet displaced a lot of the soil, and guess what you're looking at? A total white ice right below this lander. Yeah, very, very cold. And so, as you can see, so Mars has a lot of water.
Is it salty too?
Yes, as a matter of fact, the Martian water will be salty for the same reason ours was. Okay, and the thing that's interesting is, at the south pole of Mars, like a kilometer below the surface, an orbiting probe, I think it was Malin Space Science Systems, the Mars Orbital Camera. No, it was a radar, was able to detect water beneath the south pole cap of Mars. Why water? I thought water wasn't there, Mark. What's going on? Because the weight of the strata on top increases the pressure down below enough for liquid water to exist deep underground.
So it's like a lake?
Yeah, an underwater reservoir or aquifer or lake. Yeah.
Cool.
And that water down below is miles long, and it most likely, as you just pointed out, is very briny, salty. See, so liquid water exists on Mars too. It's just that it's locked up in a different way right now because the Martian atmosphere thinned out. Earth's atmosphere didn't thin out until it started raining, and then it reached a level of equilibrium where it is now. Right? Venus was too hot. The water could never form rain clouds and rain out. So it never rained out. Okay. However, it did, because of the sulfur content and so forth, it did go into making a lot of sulfuric acid, and the clouds are riddled with it. All right. So obviously, habitable zone, liquid water, habitable, stable star system. Okay. Our early sun was pretty energetic, but it's sort of stabilized now. But actually, it's really not as kind to us. I know we're what we call a habitable planet, but guess what? We're not super habitable. There are planets out there that'd be much better for us than this one, believe it or not. This one's always trying to kill us. Volcanic eruptions, tornadoes, hurricanes, plate tectonics making earthquakes. Oh, look out, we're all going to die. Right? I mean, that kind of thing happening too.
Wouldn't we expect that on any planet or any?
Not necessarily. A super habitable planet might not have the same type of tectonic activity we have. And so it might have a lot of water with a lot of land masses, and they might be static. And there's actually some planets that seem to look like they may be more of super habitable. They're a little bigger than the Earth, but so what? You think about, planets that are like twice the size of the Earth, and they call them super Earths. It doesn't mean they're actually large Earths. It means they're just twice the size of the Earth. So they're kind of a supersized Earth-like or rocky planet. It could all be rocky. But if it looks like the Earth, you might say, well, if that's twice the size, then gravity's going to be pretty strong. How could those things survive? How can anything survive? Go to our deep ocean, all right? on the bottom of the deepest parts of the ocean, you got little fish swimming around right out at the sand. They're down there 30,000 feet deep. At the bottom where Titanic is, it's not a dead zone. There's creatures down there living in the deep sea, always in the perpetual darkness. Bring them up, though. Bring them up to the surface, and what happens to them?
Don't they go inside out or something? I mean, don't their
Yeah.
bodies like distort and stuff?
Yeah, if you bring them up
It's sad.
and you bring them up in a container that's like an open top on it, okay, you actually find that they just go blah, 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 and they just burst, and that's really terrible. So to get a good sample, you got to keep them at the same pressure down there, and to do that, you need a specialized set of containers. And so to do that, the deep submersibles have these titanium canisters that can withstand that pressure, and it just fills with water, okay, under the pressure that it's under, and it sucks up the little creatures. And when it gets to the surface, those creatures are still intact. Now if they opened it and poured it out, it would go bleh, and that wouldn't be any fun. But so in other words, what I'm getting at is that creatures can live at all different pressures, even us. There's creatures that might say, you have like almost 15 pounds per square inch on your body. How can you live? Well, because we're evolved that way. And those creatures down there evolved that way too. So that's how that works. If we get to Europa around Jupiter, right? You have Io, Europa, Ganymede, and Callisto, the four primary, what they call the Galilean moons of Jupiter. In our Sky Tour telescopes, we always see Io, Ganymede. Io, Europa, Ganymede, and Callisto. We always see those. Well, Europa has this big ice sheath, many tens of miles thick, and then inside, because of the constant gravitational, kneading, as in kneading, like kneading bread, okay, and squeezing and tugging, the interior is very warm, and all that ice is melted, and it's probably very briny, salty. However, it turns out also that stuff in the middle, all right, it's actually at the 2,000 mile diameter moon. So they're thinking, holy cow, there might be life under that ice. I mean, we have life in the dark here, don't we?
Yep.
Right?
Thermal vents, yeah.
Yeah, the grand geothermal vents. In fact, finding life at the geothermal vents is why we started to think that maybe there's life on Europa. And even on Saturn's 300 mile diameter moon, Enceladus, which is a similar situation. Enceladus actually has active geothermal vents that we can see.
Oh, cool.
So that's pretty cool, right? So does it mean that life's guaranteed? No, of course not. Does it mean that it's possible? Absolutely. So even in our solar system, we might find extremophile life compared to us, life at the extreme. And that could be us to another life form that's here from another star. These human things are extremophiles. They live under this big, thick atmosphere and not in space like us. Oh, how do they do it? Right? So a lot of things, So I've told you about the habitable zone, and I told you about the liquid water, and I told you about the stable star, So that's pretty cool. Now it's interesting to notice that, there's many different types of stars out there, right? When I showed you before, I showed you this one image or a couple images in our media here, and you saw the different spectra of the different stars here. Okay. Each star has different elements. Those black lines mean different elements. And just out of curiosity, notice the third line down, it says Alpha Lyra. That's Vega, the star Vega, 26 light years from us. And it's an A0. And the V means that it's a normal fusion, hydrogen fusion star like our sun. Look at how thick those black lines are to the left and heading out toward the center, right, of Alpha Lyra. Okay. Those, it's well known that A-type stars have the brightest or the deepest, they call it, lines of hydrogen. That's the hydrogen Balmer series. Balmer. You have to remember this. That won't be on the test. Okay. So the Balmer series, those bright lines are actually those big lines. The A0 stars have the fattest lines, and that's kind of important. And then we have, as you see now, next you have Zeta Lyra. That's an A4, and that one actually has thinner lines. But notice that it has more lines near the middle there in the green,
that green,
right? And then the red. Now, what that means is this star has more elements in its outer atmosphere that are absorbing energy. All right. And Vega,
Newer or younger, or you
well,
can't tell from me.
it doesn't have to mean that. It means that the star was made with more elements when it was made that were in the stellar nebula from which it was made. And all those elements aren't doing fusion. The only thing doing fusion is in the core, and we don't see what that's doing. We only see what's in the outer envelope of a star. The core is just it's burning hydrogen into helium. Then if it gets hot enough, it'll do helium into carbon, carbon into oxygen, oxygen into magnesium, and more. And then finally it gets to iron where it stops. But that's only for very, very massive stars. Okay. So the farther down this table you go, from the O stars down to the M stars, okay, the cooler the star is. All right. The stars that are really hot, and I guess I said, it's this one. This chart starts with a B star, but we did look at, we did look at these guys here, which shows the O stars up there. Okay. And it goes right through B's of the different types. And you can see the lines. And if you look at the A0 right here, okay, that A0 shows those really big dark lines. And you see that those dominate the spectrum of those A stars. Okay. So that's pretty cool. All right. So all that stuff means is that there are certain stars that are more conducive to life. Okay. So when we ask the question of can they all support life, the answer is no. Okay. On that upper left, that's the O stars we talked about, brightest and bluest. Okay.
Right.
Now there's a snaky line, this snaky line right here. See my little cursor, the snaky line going right down there.
Yep.
This is called the main sequence. You notice the sun is in here too, right here. This main sequence, this is the star. These are the stars that are actually, all they're doing in their cores are converting hydrogen into helium. That's the main
All
fusion.
they do.
That's all they do right now. Okay. All right. But when this O star stops fusing hydrogen into helium, it may expand. And if it expands, it could end up expanding into a red supergiant. These are the post main sequence, that is the post hydrogen into helium burning phases for these stars. So they can become giants based on what's happening. Stars that are like this, they're born that way. And when they get born that way, they only live a few million years and they go boom. So stars like that, okay, and I mean boom, supernova, stars like that can't support life, right? And the reason is because they don't live long enough. They don't last long enough. All right. So you see there's that relationship between the color and the temperature of these stars, hottest and bluest, coolest and reddest, right? Now it's also true that we can kind of calculate the brightest light that comes from a star through this thing called Wien's law, and this is, I won't get into Wien's law, but it just means that we can calculate what we expect coming from these stars. And what we'll find sometimes is that much of the light from these blue stars comes from the ultraviolet side of the spectrum. What that means is, like with Mars, sterility, baby. Okay. Those, if there's any planets at all, they are probably going to be sterile rocks. Okay. So that's what's important there. Now, the consensus is that stars from about A here out to M can possibly support planets. We are a G. We're a G, and then not just a G, but a G2. So G number 2, and then Roman numeral 5, because that's the V is where they belong on this diagram. The V says if they're here, like if they're in this doing hydrogen into helium, they're V, which means they're just they're called dwarfs, believe it or not. And if they are here, actually up here, they're 1A, Roman numeral 1A. Okay, so that means supergiants. Okay, and we have regular giants here, which are types 2, 3, and 4 Roman numerals. All right, and all these stars exist, but stars up here are not going to be able to have life-bearing capabilities. It's the main sequence stars. Okay, these are short-lived. These are long-lived. Do you know down here these M stars? Of the coolest M stars there are, Tara, do you know that not a single one has actually died in the universe yet since it's been born?
I did not know that.
They last
That's
trillions of
amazing.
years. Yeah, they last
Amazing.
trillions of years. Yeah. So there you see it. I mean, this is kind of the bottom line is this is the kind of thing where when we look at different stars in the universe, we see that only certain ones can support life like us. We also see that the building blocks of life, if you're in the habitable zone, come from asteroids and comets and meteors and from the planets themselves. Okay. Now, I was watching, as one of the last things I'll mention, I was watching when the Curiosity rover on Mars was doing a grind. Okay. They have a tool called the RAT, the rock abrasion tool. And by the way, I just have to say, there's a scientist at JPL that got me started in Jet Propulsion Lab that got me into astronomy. His name was Bert Lee. Bert, and his nickname Gentry Lee, and he's the head of all outer space robotic missions. He's the head engineer, and I sent my space station plan to him as a 9-year-old, not knowing it was him. I had no idea who he was. He was a NASA scientist at the time. And he wrote back and he sent me a big box full of pamphlets and mission patches and models and books. And said,
what a nice guy.
What an incredible guy, Gentry Lee. Yeah.
Wow.
And I actually talked to him 40 years later. And I said, Gentry, you got me into astronomy. And I told him the whole story about my space box. I used to revere that box, had full of all these things. And I said, thanks to you, I got very interested in astronomy and I became an astronomer. And he goes, I don't remember, but that's exactly the kind of thing that I used to like to do because I felt that children were very important to foster that. He's absolutely right. And that's why I do public outreach in astronomy today, probably because of that one man. Because I want to foster the science and get that curiosity going in the minds of people and folks. I don't get paid for this. Well, neither do you, I guess, right? So,
I'm like, oh, you get paid?
but with
It's
Sky
rewarding. It's
very,
rewarding. So
yeah,
that's
it is.
the payment. So
yeah. I did want to see. I know I had a question.
we have
from
like
someone
2
in the
minutes,
chat.
I believe.
Yeah, I know we're getting down to it.
We're getting there.
Here it is. There we go. I think. Now, when you're interested in doing astronomical outreach, one of the things you look for is what are called Messier objects. Okay, Charles Messier in the 1600s, 1700s put together a list of over 100 different objects, 110 different objects that were really cool. And he was doing it not because of that. He was doing it because he was categorizing what not to look at if you're looking for comets, which I thought was hilarious.
What not to do.
Yeah. So anyway, Charles Messier categorized these objects as objects to avoid if you're looking for comets. And it turned out they're the most interesting objects we like to look at every day now. It's really cool.
Because they're nebula, right?
Other nebula, they're clusters, they're globular clusters, there's special things, there's galaxies, really neat. But Sky to Life fan wants to know about doing a Messier marathon, which is something people do. The best method is there's a couple times a year when it's best to do that because all the Messier objects are all over the sky. But there's only a couple times a year when you can actually look at the first one and the last one and do them all in order.
Oh.
Like a couple times a year. You got to wait for, you got to wait. It's an all-nighter. You're doing an all-nighter. But yeah, so I will ask that. And even though you spell my name wrong there, okay, it's an Marc, okay. But even so, what I'll do is I'll help you with the Messier Marathon. I'll get the dates that are best to start looking. All right.
Cool.
So that's pretty cool. So I guess I have to say, you guys, I want to thank you guys for watching. This is our new spot, like I said, 8 to 10 on Wednesdays. And we'll be able to do a lot more live shows because of the fact that it's not the weekend. It was killing us on the weekend, So that said, I'm going to hang up here with you guys and with Tara. Isn't she great? Give her a round of applause. Yeah.
Great. It's a great chat. I mean, there's great questions. This is just fun.
People are great.
Opportunity. Yeah. So thank you.
Yeah. And it's always a pleasure having you on with us, Tara, and listening to everybody in the chat. And the questions are always good questions. I know I missed some of your questions, and I'm sorry about that. But I will get to answer them in our next SkyTour live stream when we actually open the telescopes. And so I'm going to open Benson tonight, but not publicly. I'm doing it because I'm troubleshooting a little camera problem.
Have fun with that.
Well, the alternative is a $1,500 fix.
Yeah.
I'm going to fix this.
Good.
So,
and
so
if anybody can, you can. So.
I'll try, right?
Yeah.
No, I don't want to send you out to Benson.
Well, I'd like to go.
I want you to
go.
It's
kind of a drive, though.
It is too long a drive. We have someone out there that can go out there. We have 2 people now that can go out there. We have a wonderful guy, David from Arizona, who goes out there to help us. Yeah. And we also have another guy out there named Glenn who will come out, and he's only 6 minutes away.
That's great.
Yeah, it's really good.
A lot of support from everybody.
Yeah. And so, and the thing that's important is that astronomy is for everyone. Science is for everyone. Yeah. Sometimes you just need it explained in the way that you need to hear it. Yeah. And that's what I do with shirts like this. Look at that.
Thank you, Mark. That was such an interesting night.
Well, thank you, Tara.
I'm curious to see what's on the back, though. So,
what's on the back is more of the same. They're all different equations. And like I said, I've used many of these trigonometric identities in the past, and I still use some of them, but not all of them. That arrow is kind of fun right there. It just sort of goes zip.
Got it, Mark. So it's time to go.
All right, guys. Well, have a good time, and we'll see you again on the next SkyTour live stream and SkyTour Radio. Good night, all.
Bye, everybody. Thank you.